Hello interwebs, welcome to Adamant IT. I've got a Lenovo IdeaPad 320S here that does not power on. It looks to be in pretty good condition. Now, if my memory serves me, when this one came in, the customer was just like, oh, it won't turn on. And so I plugged in a charger, and after a second or so, I caught the whiff of burning. I was like, whoops, let's unplug that super quick kind of thing. So I'm not going to plug this in immediately. We're going to take the cover off and just have a look. So I'm going to roll the intro while I take these back screws off, and we'll inspect the inside and see if we can spot anything. Ooh, okay, well, we've certainly got something to work with here. Hands up in chat who's already spotted this. Now there's your problem. There's a massive skid mark. Something has gone nuclear. Let's get under the microscope so we can take a closer look and see what exactly has gone nuclear and whether it's important or not. Well, something has turned itself into a ball of slag. Hard to tell what that is. Maybe a resistor? Current sense resistor? Let's get a toothbrush and just clean up the skid marks around there. And that might give me an idea as to what exactly that is. There's been a lot of heat there, though. I can see damage to the trace nearby there. You can see shiny copper. Okay, well, PL is an inductor, so that used to be an inductor. So this is a secondary power regulator. I think that was an inductor, because that's another inductor there. This might be, this might have two outputs, this guy. This might be a regulator that's doing two voltage rails, a small one and a big one, or something like that. If we move further down, we've got some more hints here. So here we've got PU501, and this is also a regulator. Again, we've got a controller chip, an inductor, and there's big capacitors and stuff like that around here. And there's PL503, that's an inductor. So this might be like an input inductor, and that's the output through the big coil. And up here, this looks like it's basically the same thing, just a larger one. So my guess is that this is the 5-volt rail, and this is the 3-volt rail. They're both functionally the same conceptual design, just one is bigger than the other because the 5-volt rail has more grunt in it. So this looks like an exploded 5-volt regulator. My guess is that we're going to find that the 5-volt rail is shorted and it has pulled too much current and exploded this inductor. So let's turn on the multimeter and take some measurements. So with our multimeter in resistance mode, let's check. Let's just go up and find our main power rail just out of interest. So here's the DC input. That's fine. Let's find the main power rail, which is probably that input, to be honest. But I'm going to go up to CPU V-core up here. These 25-volt capacitors will be on the main power rail, because there's nothing else in the laptop that's going to be at that voltage. Out of range, so that's just functionally infinite resistance there. That should be ground on that side, just to sanity check. Yeah. So we don't, it looks like we don't have a short up there. Okay, fine. So what about that then? Yeah, again, that's high resistance. So what about over here? Whoops. Okay, that looks like we found a short there. Again, it's kind of it doesn't know if it's coming or going, but can I get better probing? Ah, no. let's go onto this big capacitor just where, so I've got a nice big chunk of metal to measure on. Okay, there we go. Yeah, so that's basically shorted. I'm going to call that less than an ohm, I think. So we've got a short circuit here. I'm assuming we're going to find it here at the output as well. Oh my god, could I stop falling off of everything? No, interestingly, the output isn't shorted. Oh, is it just a dead regulator? Has this regulator just decided to go short circuit and explode itself? So it looks like this chip has internally failed and gone and has shorted its input to ground. And then that has created a dead short circuit at the main power rail coming in, and which has just caused this input inductor to go nuclear. This guy failed and went bang before this guy could go nuclear, basically. So it looks like we just need a new one of those. What are you? BAC 7MB. Not seeing a lot of results on Google there. Okay, let's see if we can find a schematic for this board, because then we can just pull up the model number of the chip instead of the markings on the chip. So this is an LA-E541P. Right, so here's our schematic for this board. So the chip that has exploded is PU502. So let's search PU502. All right, that puts us here. Cool. So if we have a look at these outputs here, we've got our 5-volt rail. So I was bang on the money. That is indeed the 5-volt. And then the one above it is the 3-volt. So yeah, I was basically bang on the money with that, which is fairly obvious when you know your way around a motherboard. This one was a really nice, clear example of the 5 and 3-volt rails. And if we have a look here, PL504, this is the guy that's gone exploded and melted down. So that's gone bang. And this is it's EMI protection. That's essentially what this is doing. And so that is it's doing EMI protection, but also in this case, it's also functioned as a poor man's fuse. So this guy here has internally shorted itself down to ground, causing it to pull infinite current until something explodes. And if we have a look, this is an SY8288. So let's search for that. Let's start with that first bit. We might need CRAC, but I'm going to Google for that first. That looks like a yes to me. Let's check it. 8288 CRAC. 8288 CRAC. £4. Delivered by the weekend. Alright, I'm going to take a swing at that, I think. But before I hit the buy button, let's just remove the damaged components and make sure that there isn't a crater in the board that's going to cause us a lot of heartache. So I'm going to go ahead and put down a little bit of heat and flux on this. Take that chip off the board, take the inductor off the board, and just check if we've got any more serious damage to that. Some of those traces look a bit delicate, but I think those will come good. So here we go, everyone. Right, so we've got some PCB damage there where the inductor went nuclear and burned a hole in the board. It doesn't look like this area of the board is particularly congested though, so we'll do some measurements. With the chip gone, we should find that our short circuit is also gone. So let's test that. So our input should still be high resistance. Yeah, mega ohms slash infinite a lot. Let's just check up here as well. Yeah, mega ohms. And this bit. Oh. Is it you? Did I run before I walked? I think I did. What an idiot. What an idiot. It was right there in front of me. You know, I don't know why I was so eager for it to be a regulator there. Like, it's always a capacitor. I should have gone straight for the capacitor. But for some reason or other, my brain just went straight for, oh, it must be a bad regulator, even though the regulator itself hadn't gone bang. I don't know what part of me thought it was the reg. Okay. Let's take off that capacitor, shall we? Why did I think it was the... Oh, it doesn't matter. It doesn't matter. Why did I think it was the reg? Alright. And in a surprise to no one, with the really obviously busted capacitor off the board, we're no longer shorted to ground. What an idiot. Okay. Right, so we've got a busted cap, and so before I spotted that capacitor and that we were still shorted to ground, the next thing I was going to do was check the actual chip itself. And let's do that anyway, because what we're now going to find is that this chip is completely fine. So if we have a look at the layout for this, we've got our input pins here, and we've got ground pins up here and in the center. So if I flip this chip over, and if I check from these pins here to the ground pad, we should find that there is not a direct connection through there. If this chip had been faulty like I thought it was for some bizarre reason, we would find that this is shorted through. However, as you can see, there's no connection through there. This thing is completely fine. There's too much solder. We'll tidy that up in a sec. Just holding the chip steady with the tweezers while everything starts flowing. Now we can just let it dance on the pads until it aligns. And I'm going to press it down because we've got about 10,000 gallons too much solder in there. Right, and now if I just run the iron around the sides, we should be able to pick all of that up. Yeah, those pins are common together, so it doesn't matter that they're bridging. No need to sort that out. So our capacitor is going to be one of these guys. There's 4 capacitors here. I only see 3 of them on the board, but some of them might be a no stuff. So we've got 2 10 microfarads. We've got a 2.2 nanofarad, 2200 puff, and a 100 nanofarad. And if we compare this with what we actually see on the board, you can see here we had 2 big ones. So these are both 10 microfarad capacitors. Dead easy. We've got stacks of those. Then there's a small one here and a no-stuffed capacitor here. So my guess is that one of those they decided just wasn't necessary and isn't on the board. And the other one is going to be whatever the other one is. So, however, these are the ones that matter. They're 10 microfarad 0805s. So I'm going to grab me one of those and put that on the board. Then we also need a new inductor. So I'm going to do a bit of searching around and see if I can find one of these on a donor board. These inductors are not super mission critical. Theoretically, I could just solder blob this guy out. However, I believe in replacing components where possible, so I'm going to see if I can find a replacement one. This one might be optional, but the next one you come across might be critical. So it's good to practice replacing components with the right ones, because then when it does matter, you'll be ready. And now and then, if you get caught short, fine. However, if you can replace, you should replace. That's what I think. So what this means is that this inductor, or in this instance, it's so small that it's also known as just a ferrite bead, because it's barely an inductor at all, but it functions as one. So what this does is it is filtering out noise on the line. So this line should just be carrying a steady voltage, but there's going to be high frequency switching noise and EMI and radio signals hitting it and stuff like that. And what's going to happen is that if you get high frequency clutter up at, in this case up to 25 megahertz, then it will have an impedance of 120 ohms. So for just a straight DC voltage, it will do nothing. But any high frequency clutter on the line, any high frequency switching noise that's causing ripple up in the megahertz frequencies will start hitting up to 120 ohms of impedance, which will effectively filter it out. I think I'm explaining that right. Then the last bit is 5A basically means it can handle 5 amps of current. So that's my interpretation of this. I think this particular way of writing can vary a little bit. But what I'm going to do is I'm going to see if I can find one on a donor board, and then we'll see if the markings are similar, and then I can show you how I figured it out. Right, I've done some scrubbing about, and on the on Apple MacBooks, they typically label these ferrite beads as FERR, then 70 ohm 4 amp. So that's going to be 70 ohms 4 amps, and this again is going to be in the megahertz range for measurements. So in order to actually find stuff, my search term was just -ohm-, and then I can just press N to cycle through all of the beads on the board until I find something that looks like it's in the right ballpark. And there were quite a few. It was quite easy to find a 120 ohm 3 amp inductor. However, we're looking for a 5 amp. Now, I think 3 amps is probably going to be good enough, because 3 amps, that means up to 15 watts on the 5 volt rail. That's a quarter of the laptop's entire power budget, including battery charging. So, I can't see a world where 3 amps wouldn't be enough, but also, if it's not enough, we'll blow up the replacement part. So, what I'm going to do instead is go for this 4 amp one that I've found, because that's definitely going to be enough. It's rated for 70 ohms, not 120, but that's still going to be good enough. In the real world, the regulator itself will probably cope with most general ripple and interference anyway, because of robust standards of circuit design. You build overkill, basically. So we can go a little bit lower on the filtering in order to get that 4 amps of current rating. So I'm going to steal this. It's L7500. It's down there. Okay. Right, let's put this on the board. So I will stick a solder blob on this side. Well, in conjunction with the one that's already there anyway. And let's merge this guy into said solder blob. Right, I don't think there's a world where this is going to sit flat on the board, purely because the actual pad isn't flat. I'll give that a reflow with some flux in a sec. Let's put some solder on the other side of it. It's going to be really ugly, but I could try and, grind down the surfaces and make it look pretty, but sometimes less is more. I think I'm just going to stick a solder blob in there and send it. There we go. Maybe that'll give it the extra current handling. Okay, and up here we need a new capacitor. So I'll put a solder blob on the top pad. That's immediately going to jump over to the other capacitor because everything hates me. And here's a nice shiny new 10 microfarad capacitor. It's even the right size as a special treat. There, that's sticking to the other one. Can I unstick that? Just for tidiness' sake. Cool. Okay, there we go. So our inductor is kind of hideous. However, I'm not going to mess around with that pad. It's functional, is how I'd phrase that. And we have replaced the capacitor with a shiny new one, so it's got the appropriate input capacitance there. We'll just double check that we haven't magically managed to short ourselves to ground in the process of all of that. So if we just check that. And yeah, we've got very high resistance. Beautiful. So on the assumption that I didn't balk that regulator, taking it on, off and on the board again, we should find that we can switch this on and it works. So I'm going to grab the laptop chassis, slap this back in the laptop chassis, and it should power on. Right. Carefully open this because the back is off, so the hinges are not supported. Right, and DC in. Please don't explode. Okay, we've got a power line. The CPU fan twitched as well. And it's probably RAM training. Oh, there it goes. Excellent. That seems to work just fine. Alright, and there's a charge light on the side. Now the battery's plugged in. And we should find that this will boot all the way into Windows now. So, actually a very straightforward repair. It was another dead capacitor, because you love to see it. And that would have been a really straightforward textbook case. There was a massive arrow pointing at the fault, and the capacitor that we took off looks dodgy as hell. But for some reason or other, my brain just went another direction, and I don't know why. However, thankfully I spotted it before I just immediately went on to some other tangents there. I was ready to just go and buy that chip and put all of this to one side until it arrived. But thankfully, I just had that moment of clarity where I was just like, hey, maybe I should take the faulty components off the board and double check that that's actually going to fix my problem. And I think therein lies the brightness is low, but as you can see, it's booted up. And I think therein lies the lesson of this video, is when you think you found a solution, you should actually take a moment to assess your solution and ask yourself, is this going to solve my problem? And why do I think it's going to solve my problem? And can I prove that it's going to solve my problem? Because that might just help you catch yourself before you do something really stupid like I did there. However, no harm, no foul. That's one fixed laptop. Thanks for tuning in, and I'll see you next time. Bye.